First of all, welcome everyone, and thank you so much for joining us. We are so excited to have you all in this webinar. I would like to start by talking about Space Generation Advisory Council, which is the organization we are part of, Angel Arcia and myself. Space Generation Advisory Council, in support of the United Nations Program on Space Application, is a non-governmental, non-profit organization and network which aims to represent university students and young space professionals ages between 18 and 35 to the United Nations Space Agency, industry, and academia. I would like to also mention some of the activities we have been doing in collaboration with the NPOC, or National Point of Contact Panama, and National Point of Contact Nicaragua, which is myself. And we have been doing the Space Speaker of the Month series with different topics related to space. We have the open course Introduction to Space Engineering, where we have students from Nicaragua and also from Panama. And in Nicaragua, we had also this webinar with the engineer, Sandra Kaufman, who talked about engineering and her experience as a woman in the space industry. So after all this, I would like to hand it to Angel Arcia so he can introduce our guest speakers, and so we can continue with the webinar.
All right, thank you, Roxy. My name is Angel Arcia. I am the National Point of Contact of Space Generation for Panama. And it's always a pleasure to be doing this kind of webinars and workshops for the Central American, Latin American, and global network of students. So we have very special guests today. First, we have the Dr. Luis Rabelo. He was a previous project manager at NASA, 2009 and 2011. He's currently a professor in the Department of Industrial Engineering and Management System at the University of Central Florida. And he's also an electrical and mechanical engineer from the University of Technological University of Panama. We will have also a very special guest. With us is joining us Mike Conroy. He's an electrical engineer, and he was a NASA modeling and simulation project manager, and also in charge of the Florida Space Institute FSI student design projects for students. And later, Laura Segarra, she will join us in a couple of minutes. She's an aerospace engineer, and she belongs to NASA commercial crew. For all of the participants, we will have a live or simultaneous translation from English to Spanish. Dr. Rabelo will start his speech in Spanish, and I will be translating to English. So you can click in the icon in the Zoom tool that it says interpretation, so you can hear the simultaneous translation from English to Spanish. Dr. Rabelo, the audience is yours, and it's always a pleasure to have you here.
Okay, vamos a hablar de qué es la NASA realmente. Ese es el objetivo de esta presentación, como una organización a la que yo conocí en el 2009-2011. La de estos momentos es un poquito diferente, pero muy parecida. Yo diría que 75% parecida a esa NASA que es todavía del periodo del Shuttle. Así que siempre hemos tenido contactos con aeroespacial. Cuando trabajamos en BF Goodrich, mi grupo también trabajó con el X-33, que fue un proyecto tratar de hacer un transbordador que fuera directamente desde la Tierra, sin ayuda de otros cohetes, a la estación espacial y regreso. Y BF Goodrich era la que estaba encargada del sistema protector termal. Y también en Honeywell, mi grupo de sistemas de control también estaba a cargo de la parte de control del X-38, que era un salvavidas para la estación espacial, pero que el proyecto se paró en el 2002. Y bueno, también en este sí trabajé como consultor directamente para hacer simulaciones con Boeing Phantom Works en el 2003, para otro proyecto que fue cancelado, que se llama Alternate Access to Space Station. Y bueno, con NASA, siendo un NASA Fellow, trabajé en un proyecto con NASA Ames. Trabajé en el Return to Flight como NASA Fellow también, y trabajé en el NASA Tiger Team del transbordador aeroespacial modelando la parte térmica de los del transbordador, y también trabajé con la Oficina de Recursos Humanos modelando con agentes de simulación cómo la gente se envejecía en NASA y cómo eran los ingenieros, cuáles iban a ser las cosas potenciales. Bueno, así que vamos a hablar un poquitito de la Universidad de la Florida Central, bien rápido, de dónde somos. Del año 2009 agarré la visión y misión de la NASA. Toda organización, toda compañía como Coca-Cola, etcétera, etcétera, tiene una visión y misión, así que les voy a hablar de esa visión y misión de la NASA. Vamos a hablar de la estructura organizacional antes del año 2011, para que vean los diferentes divisiones de la NASA y cómo trabaja en una estructura matricial. Y entonces hablaré un poco de lo que hemos hecho últimamente, y así que vamos a ver. Así que Universidad de la Florida Central es una de las universidades más grandes de los Estados Unidos de Norteamérica, o quizás la más grande, que tiene 70,000 estudiantes en el campus, un campus de más de 1,000 hectáreas, con más de 200 edificios, y el tráfico es tremendo dentro de la universidad. Hay no sé cuántos semáforos, y hay cuellos de botellas y problemas con el tráfico en la universidad por la cantidad de estudiantes y la cantidad de profesores y todo eso. Y entonces ha estado avanzando últimamente la universidad, y al lado de la universidad quedan muchas compañías trabajando en simulación. Y se dice que Orlando es la capital de simulación del mundo. Hay más de 17,000 ingenieros en Orlando que trabajan en simulación. Hay compañías que hacen parte del juego FIFA de la Sony PlayStation. Hay gente que hace partes de Disney, y por supuesto todos los simuladores del Departamento de Defensa son hechos en Orlando, y está al lado de la universidad. Y bueno, ese es UCF, un clúster de tecnología, y hay algo de Bill Clinton hablando de eso, pero no lo vamos a poner el día de hoy. Así que vamos a ver qué dice esta visión y misión de la NASA. Y a mí me gusta esto porque me emociona leer la de esa época. Dice la visión, para llegar a nuevas alturas de excelencia y revelar lo desconocido, y para que todo lo que hacemos y aprendamos beneficie a toda la humanidad. Y la misión dice, entonces ya esa es la visión. 5 años más adelante, eso es lo que quiere hacer la NASA, 5 o 10 años. Pero ahora, ¿qué es lo que los define? Dice, avanzar las ciencias, la tecnología, la aeronáutica y la exploración espacial para mejorar el conocimiento, la educación, la innovación, la vitalidad económica y la superación del planeta Tierra. Espectacular. Visión y misión de la NASA. Eso es lo que define a una organización. Ejemplo, en el año 2000, la visión, y eso siempre cambia, esto ya no es la que está en estos momentos, eso sí, cada 3 o 4 años la visión y misión de una organización cambia. Por ejemplo, Coca-Cola, cuando se hablaba de globalización en el año 2000, la visión de NASA era bien sencillita, la visión de Coca-Cola era bien sencillita. Decía, una Coca-Cola en todas las manos del mundo. O sea que cada mano del mundo, los chinos, todos, los hindúes y todo, la visión era que cada uno tuviera una lata de Coca-Cola en la mano. Y eso, entonces, pero la de NASA es espectacular. Así que la NASA que yo conocí, es que hay que estar yendo a la casa matriz para ver cómo trabaja esto. Y entonces, básicamente, en la casa matriz hay 4 directorados de misión. Podemos decir que 4 divisiones. Hay una división, y hay miles de personas trabajando para esa misión. Está la misión de investigación de aeronáutica, solo de aviones. No estamos hablando de cohetes ni de nada. Aviones, cómo incrementar la tecnología y avanzar la aviación desde todos los puntos de vista. Hay otra división que es la de ciencias. Y ya vamos a hablar mucho más de esa. Esa es puro ciencia. Físicos, biólogos, geólogos. La anterior, la de aeronáutica, es totalmente, los dominantes son los ingenieros. Los ingenieros aeronáuticos, los ingenieros mecánicos, los ingenieros de sistemas, psicólogos. Para diseñar la pantalla de un avión se necesitan psicólogos. Tenemos entonces otra división que es la de exploración y operaciones. Y esa es, generalmente es en Houston, esos están viendo cómo va a ser la exploración humana. La palabra humana es la clave, no robots, humano, mandar astronautas. Y ahí hay muchos ingenieros, también hay muchos médicos, porque mandar un humano, Dios mío, eso es el corazón, todo eso. Psicólogos, nutricionistas, ¿qué clase de comida van a comer? Ese es Human Exploration. Y tenemos la cuarta, la división de tecnología espacial. Estos son la mayoría, y de ahí viene Mike. Esos son ingenieros que esos lanzan cohetes. Eso es lo que les gusta, lanzar cohetes. Y entonces esas cuatro divisiones son las que tienen el presupuesto y de acuerdo a los proyectos es que mandan dinero a los diferentes centros de la NASA, que son 10 centros. Y vamos a hablar más de eso. Entonces vamos a empezar a hablar más. Por supuesto, la casa matriz está en Washington. Ahí es que está la plata. Desde ahí es que se reparte la plata. Desde ahí Trump decide qué presupuesto va a tener la NASA. Y el presidente Trump ha sido muy bueno con la NASA. Nunca le ha cortado el presupuesto. Así que ya vimos desde la casa matriz en Washington y ahí tenemos la aeronáutica, el sistema de exploración humana, ciencias y operaciones espaciales. Ahí ven los cohetes lanzándose. Y acá la exploración del futuro, y acá la ciencia y la aeronáutica. La aeronáutica ha dado tantas contribuciones al mundo. Eso es lo que la gente nada más ve en los cohetes. La aeronáutica son ingenieros que tienen túneles de viento y hacen unas contribuciones gigantes a los aviones. Por ejemplo, todas esas son contribuciones al mundo de la aeronáutica sin cobrar dinero que han hecho. Cuando ustedes ven los aviones de copa, por ejemplo, que vuelan, tienen estos winglets. Los winglets fueron inventados en la NASA en 1973. Las torres de controles, el software, muchos de los software que hay, las pantallas, la forma de las alas, materiales, todo eso viene de la NASA. El tráfico de control, los TRACONs, todo eso viene de la NASA. Estos son puros ingenieros aeronáuticos, ingenieros electrónicos, psicólogos, todo eso. Pero nada más es aviación. Y entonces hay muchos centros que se dedican a esto solamente. Así que estos ingenieros son los más especialistas del mundo en esta área y las investigaciones revierte a toda la aviación mundial, a la Boeing, al Airbus y a todas desde aviones pequeños y todos. Más bien el brazo de investigación, el brazo de investigación de la FAA, la Agencia Federal Norteamericana de Aviación, es NASA. Así que esa es la parte aeronáutica, solo aviación y muchas contribuciones. Y por supuesto, proyectos espectaculares hay en esa división y que va a muchos centros de la NASA. Tenemos ya la dirección de ciencias. Esos son científicos que hacen muchas cosas. Ejemplo, el rover que acaba de salir viene de la dirección de ciencias. Los proyectos de mandar un rover, no humano, o rover y eso, viene de la dirección. Buscando vida en otros planetas, viene de la dirección de ciencias. Esta división de ciencias tiene 4 subdivisiones. La vamos a explicar en el momento. La primera subdivisión se llama Earth Science, ciencias de la Tierra, ciencias terrestres. Esa gente nada más se dedica a la Tierra. Hay vulcanólogos, geólogos, hay gente que estudia el cambio climático, por ejemplo, hay en NASA. Gente que estudia el deshielo en el Himalaya. Hay gente de NASA estudiando eso. Y puede que interactúen con otras divisiones para con satélites estudiar la Tierra, por ejemplo. Hay otra subdivisión, muchos físicos, que es la heliofísica. Estos nada más se dedican a estudiar el Sol. Solo el Sol. Hay gente especialista en terremotos del Sol. Entonces está la ciencia de los planetas. Todos los planetas. Venus, el planeta Marte, Urano, Neptuno. Hay geólogos, hay vulcanólogos, pero solamente estudian los planetas. Y por supuesto, la cuarta subdivisión, la última de la de ciencia, son los astrofísicos. Esos estudian todo lo que es más allá del sistema solar. Los huecos negros, etcétera, etcétera. Así que ya vieron que la NASA no es solo mandar cohetes, y esto está relacionado con los cohetes, porque quizás del presupuesto tengan que lanzar un cohete para investigar el planeta Marte, o mandar una sonda a Plutón, perdón. Entonces, todas trabajan en sincronización, pero de donde viene la idea de que es respectivo con la ciencia, es de esta división. Y por supuesto, aquí la mayoría son físicos, biólogos, vulcanólogos, la astrofísica, un montón de físicos, heliofísica, montones de físicos que no tienen que ver nada. Quizás algunos de ellos ni siquiera han visto un cohete lanzándose. Y por supuesto, la tercera, operaciones espaciales, estos saben de cohetes. Esto es lanzar cohetes, las estaciones espaciales también era parte de esta. Y entonces ellos ofrecen servicios a las otras divisiones para lanzar el satélite y todo eso. El que va a la luna, o etcétera, etcétera. Pero esta gente es experta en lanzar cohetes. Y muchos ingenieros. El factor dominante son ingenieros. Hay ingenieros aeronáuticos, mecánicos, eléctricos. Por supuesto, hay científicos, pero más ingenieros con maestría, doctorados, o ingenieros con muchísima experiencia. Y por supuesto, el transbordador aeroespacial, por ejemplo, era parte de esta división. La estación espacial, el transbordador y los servicios espaciales de lanzamiento, launch services. Y por supuesto, entonces hay un montón, que esas 4 divisiones influyen en cada uno de los 10 centros de la NASA. Ejemplo, en operaciones espaciales en esa época, los centros que más estaban con esa división, no significa que era solamente esa división, tenían proyectos de las diferentes divisiones, era Johnson, Marshall, que fue el que fundó Von Braun, Kennedy Space Center es un centro operacional de excelencia, Stennis, que se encarga de la propulsión de los motores. De la parte aeronáutica hay centros que son muy especializados en estudiar los aviones y la aviación desde todos los puntos. Está Langley, que está en Virginia. Está el Glenn Research Center en Cleveland, Ohio. Y está Dragonfly Research Center, que está en California. Desde el punto de las ciencias, Goddard es el principal, con más de 3,000 científicos, con doctorados en física, etcétera, etcétera. Biología, todo eso. Está Ames. Ames es híbrido porque también trabaja, es el centro de excelencia de la NASA en informática. Es el centro de excelencia de todo. Y está el Jet Propulsion Lab, que a veces se encarga de estas misiones espaciales de ciencias planetarias. Y entonces los sistemas de exploración que son humanos, tenemos de nuevo a Johnson, Marshall de nuevo, que diseña cohetes, el Kennedy Space Center, el Stennis de nuevo, y el Ames también se dedica a eso. Así que esas 4 divisiones apoyan proyectos en cada uno de los centros que hay en la NASA, que ya dijimos que son 10 centros. Está Johnson, que está en Texas. Tenemos Stennis, que está en Mississippi. El Centro Espacial Kennedy, que lo tenemos aquí a 39 millas, un poquito más lejos en la Florida. Tenemos Goddard, que queda en Maryland. Tenemos Langley, que queda en Virginia. Glenn, que queda en Ohio. Dryden en California. Ames en California. JPL en California. Así que casi la mayoría de los estados fuertes están representados en la NASA. Y eso es bueno porque diversidad y también el apoyo del gobierno de los diferentes estados en los que están estos centros, que proporcionan mucho trabajo y mucha prosperidad económica. Así que eso básicamente es la NASA. Después del 2011 ya hubo cambios, como ya el transbordador se había retirado, ya entonces la exploración humana se unió con la de operaciones espaciales. Y crearon una cuarta nueva, que era una misión de tecnología, de pura tecnología, que antes era una oficina del Chief Technology Officer, del oficial, del ejecutivo de tecnología. Crearon una cuarta división de eso. Así que esto es la NASA que yo vi antes del 2011. Así que cuando hablamos de la NASA no podemos hablar de Kennedy solamente o de Johnson en Houston. No solamente podemos hablar de los ingenieros aeroespaciales, que los ingenieros que ponen el cohete y lo lanzan. Es una organización bien compleja. Y vieron la misión, sin embargo, cada uno de ellos contribuye a la misión y están alineadas de tal forma que todo contribuya. Y por supuesto hay profesionales de todas las gamas. Como dije, yo conocí en Johnson nutricionistas, médicos. ¿Por qué? Porque la radiación, vas a mandar un humano. Los problemas fisiológicos, psicólogos. Y de eso cualquier día podemos conversar de las opiniones que escuché de psicólogos. Así que esa es básicamente. Y bueno, Kennedy, ya Mike nos hablará más. Y entonces, en los últimos años sí trabajamos con NASA Ames en Big Data y Medicina, un proyecto interesante. Con Mike Conroy acerca del modelamiento de la base marciana. Tenemos muchos proyectos con ULA, que es la competencia de SpaceX. Hemos hecho sistemas de inteligencia artificial en los últimos años con gente de la NASA para ver malfunciones de los rockets. Y tenemos proyectos de ingeniería de confiabilidad de sistemas espaciales. Ese otro día podemos conversar de los proyectos y de esas cosas, pero hoy quería de lo que yo conocí en el 2010, 2011, yendo a Washington y hablando con muchos de esos físicos, por ejemplo, de heliofísica. Yo no sabía nada. No sabía nada. Que había que ser un experto en heliofísica, un doctorado, que saben de los terremotos y algunas de las cosas que hay preguntas que todavía no sabemos. me acuerdo que un heliofísico me comentó que la temperatura en la corteza solar es más alta que la temperatura dentro del Sol. Y había preguntas que todavía no tenemos respuesta. Y cada vez estamos aprendiendo más. La distribución del agua en el sistema solar, etcétera, etcétera. Ya es ciencias planetarias, los cometas, todo eso. Así que yo solamente les quería decirles que era la NASA. Y entonces ya Mike nos va a hablar de su experiencia y nos va a motivar con ingeniería.
Thank you so much, Dr. Rabelo, for this amazing presentation. We learned a lot of things about NASA, and we see NASA from a different perspective, as you were mentioning. Now we would like to hand it to Mike Conroy to present his presentation.
Good morning, everyone, or good evening, everyone. Tonight, I would like to share some of the things that went on. I was blessed to be a part of NASA. The time I spent out there was an absolutely incredible journey. I'd like to share some of it, what we did, where we ended up, and along the way, talk maybe a bit about the people that helped me and the people I was able to go help. One of the things I learned very early, and the key to success was finding somebody to help and being able to go help somebody with what they're trying to do. Discussion tonight, or what I'd like to go talk to tonight, is about working together to go do a lot of things. In the beginning, I'd like to introduce myself probably a little more. That will go help. So who am I? My name is Mike Conroy. I'm with the University of Central Florida, the Florida Space Institute, and I work mostly with students doing senior design projects. I work with them as they're finishing their engineering education and trying to connect them to projects and things that they can go do that will get them more and more and more ready to go to work. Before I did that, though, I spent 35 years, fantastic years, with NASA at the Kennedy Space Center. Dr. Rabelo talked about various different centers and everywhere else. I was born in Florida, and from what I can see, it gets cold at all of the other centers, so I didn't leave. I don't like being cold. Before that, I went to college for electrical engineering degree. I was actually at the University of Central Florida when I went to school. Before that in high school, and I wanted to be an engineer. I knew that very, very early that engineering was something I wanted to go do. When I said very early, I meant very, very early. This picture is Apollo 8. It was the first lunar launch. The young kid with the hat had a great deal more hair than I do right now, and it was a bit darker than I do right now, but that's me watching Apollo 8. I was born in Orlando, Florida, and I grew up near the space program. I was there. I was able to go see it and watch it grow. From the point that I saw this launch, I knew that I wanted to go work on space. It just took me another 15 to 18 years to figure out how to go make that work. But that was my guiding force through my grade school, through my high school, and through my college. So I was very lucky that I was able to go see this. I wish I could somehow share what those feelings were and share those types of things with everybody. It was just incredibly motivating and just absolutely wonderful. When I finally got to Kennedy Space Center, when I was still in college, I was working out there. I helped with the rockets. I was given a chance to be a part of the Delta launch team. The Delta rocket is over on the right. It's one that's done 350, almost 400 launches of various payloads for NASA. I got to help worry about the second stage. I had an incredible amount to learn. It was very little that I could go add. People were teaching me. I had very, very good people that taught me, and I learned everything that I could from them and tried to help any way that I could. When I came to work for NASA full-time, I was working on the Space Lab. The Space Lab was what they put in the shuttle payload bay to do science. It gave you a laboratory in space that people could work in without having to go be wrapped up in a spacesuit. Let us do a great deal of things. It flew back and forth in a space shuttle. The team I was in, we had a lot to go learn. Unfortunately for us, this was the first time any of this had ever been done, so we had to work out how to go do everything we wanted to go do by ourselves. It was an incredible journey, but this was the first time it had been attempted, and what we did is we learned things as quickly as we could. We taught the person next to us what we had learned, and they shared, and together we learned enough to make everything work and to be able to go make things happen the way they needed to. I got a chance after that to go help with the space shuttle. The space shuttle is what made all of the science happen, all of the experiments that were done, everything that we learned. It got us to space, it gave us a place to stay, and it got us back. I worked on how to maintain and repair the electronics, all of the computer boxes and the devices that were in the shuttle. I helped go rebuild the way that we test those. I took what I learned from working with the science and working with the experiments, and I was able to go apply that and show it to people. I still had a lot to learn, but this was the part where in working with a large number of people and learning everything that I could go learn and in doing all of that, I was finally able to share some of what I learned back. I got to the point where I could share and teach some people some things, and we could all work together to go make things work better. I also worked with computer systems. By that time, I was a manager. I'm still not quite certain how they did that to me, but one Monday morning, I was a manager over a group of people, and I had a large computer system. Computer systems then are not like what we're looking at now. The internet existed, but just barely. I had one of the gentlemen in my labs was actually working on building the internet and working on the computer protocols and the network protocols and how everything went back and forth and worked on it. So this was in the very, very, very beginning. I still had a lot to learn, but I was beginning to have things that I could teach, and I was beginning to have things that I could share with others. And that to me was a very, very powerful time. The feeling of being able to go help somebody succeed, go work with somebody to help the group move forward, as opposed to just, sitting there and doing this little piece, was incredibly powerful. You notice there's kind of a theme here. I look at my career as when I could start paying back and when I could start giving things. And that was to me, the best motivation for everything is how can I learn enough to go help somebody else? Some of the stuff Dr. Rabelo mentioned is when we were looking at going to the moon in the Constellation program, I helped work the modeling and simulation. This was another one where that was a Tuesday morning, I found out that I had a new job, which was all of the modeling and simulation for the Constellation program across all of the NASA centers. Space stuff is very, very large. Things that go into space, the rockets are very, very large and they have a lot of parts. At the Kennedy Space Center, we got really, really good at putting those big parts together because they all came in pieces. So we learned a lot about how to go put things together. We also learned a great deal about how to design and build things so that they could be put together. Most of that learning came from receiving things that could not be put together. So it was painful to learn those things, but it let us be able to help people build things that could go work better. And we ended up leading things. And now suddenly we were the ones teaching others. And they were learning from us about the new tools and new capabilities and how we did things. And it made it one very, very large team. And we shared what we were good at, others shared what they were good at, and we had plans to go to the moon. Things change. We got told we're not going to the moon, we're doing something else, but the work that we did there and the types of things that we're doing there are still being done today, and it's still going forward, and we're using all of those capabilities for the path back to the moon. I helped plan and work for getting to the moon and Mars. That was one of the greatest things I've ever seen, greatest things I've ever been a part of. I retired and took the job that I've got now, working with students and helping teach before we got back to the moon. But I have no doubt in my mind that the generation of the people that I'm talking to here, y'all are the ones that are going to go get to the moon. You will get people to Mars. I think that's going to be grand to go sit there and watch. Your grandchildren will likely be the ones that get a chance to either live on the moon or live on Mars. I think that's incredibly powerful, and I think that's wonderful. But the thing that helped the most is, or helped me the most, as I went through this process and through this journey and seeing these things, was being able to follow good leaders. So both being able to lead people and being able to follow people were the skills probably that helped me a great deal in many of the endeavors I had. And sometimes I was leading tasks and people on my teams were leading other projects. but the result was they had the ability to go follow what I needed done. And it may be later in the week, those people were leading teams that I was on and I was following what they did. The ability to move back and forth out of those roles, I think, was a very, very positive and very, very powerful thing. So what have I learned? What can I share? What do I hope will be useful? I'm going to share a couple of things. This is what I told engineers at NASA, and this is what I tell engineering students when I work with them and talk with them and lecture today. An important rule: space is hard. Space is very, very hard. We need to learn to play nice with each other. Everybody needs to go work together and do it nicely and take care of each other. The game we're going to go play nice is space. It's multi-decade, tens of years, not hundreds of years yet, but tens of years of very, very large, very, very complex designs of things, development of things, and operations of things. The environment we're doing all of this in is very, very hostile, is very, very unforgiving. Space doesn't really care if you succeed or fail. It's not going to go help you in any way, shape at all, or form. But we have a very, very gifted, diverse, and distributed group of friends that can come help us with this. I worked with people across all of the NASA centers. I worked with people in the European Space Agency and in other countries, and the Canadian Space Agency in different areas. I had groups of people that were working with Japan. And everybody was working together, very, very spread out, but the goal was to get us humans, us people, as far from Earth as possible and to do it safely. That was the game: get as far away from here as we can. The rules that we had to deal with were very, very harsh to govern this game. We had to deal with physics. We had to deal with teams and processes. We had to deal with the science. We had to deal with the story of what we were trying to do and how we could describe it. Things that made it hard were the time that we had to accomplish these goals, the distances we had between each other, the cultures, various cultures. We had to go learn enough to be able to go work with each other, or at a minimum, not cause problems for each other by not understanding the cultures that were there. We had to understand the goals of all the people that we were working with, and we had to understand generations. I'm old. I worked with a lot of people that were younger than me, and at one time I was a young person, worked with who was older with me. The way we look at things, the way we understand things, and the education that we had that put us where we are is very, very different as you go through the generations and as you look at different groups of people. So how do we play nice? How do we work across time? How do we work off space to get to Mars and beyond that? The very first thing we've got to go do is understand. In my case, I understand my challenge. You have to understand your challenge. What is it you're trying to do? And as engineers and as scientists, you have to make sure that you understand what it is you're trying to go do, and you have to understand it well enough and sit down and write it down well enough to be able to share with someone else, because that makes the second step easier. You have to understand the challenges of all your friends. You have to understand what the people you're working with are trying to do. The easiest way to do that is be able to share it very, very efficiently. And if they've done the same thing, then you can understand what they're doing. So you have to understand what you're doing. You have to understand what everybody you're working with is doing and share it. And then with all of what you're doing here, you've got to share it, and you have to go leave a record for the people that aren't there yet. I started projects that are still going on. I'm not going to be there to finish them. When we're talking about a colony on Mars, there's a good possibility at least Lewis and I aren't going to be alive when that happens. The rest of y'all, I think, are fairly young. But that's going to be a difference. So we have to leave behind a record of what we did so that others can do it and we can go forward. If we do this, if we understand our challenge, if we share our challenge and understand the challenges of our friends, and we share what we do so that we can leave a record, then we're all working on the same problems. We can help each other, or at a minimum, not do something that hurts somebody else's progress. And the people that come after us can figure out what we meant and what we tried to go do, and build upon that to go forward and go forward. So if we did all of this and it all came together like this, kind of what would it look like? Dr. Rabelo mentioned modeling and simulation. From an engineering point of view, we model things. We simulate things when we make decisions. For a model, a thing that we're going to go look at, we represent it. If what I'm modeling is, or what I'm concerned with, is a coffee cup. Zoom is hurting me. If I do a coffee cup, if this is what I'm concerned with, I've got a model of what it looks like, and I have enough detail that you can recognize the coffee cup when we go talk about it and we go work with it and we can go study it. We simulate things. We simulate the behavior, how something is going to go act. And we simulate how this coffee cup would work in as much detail as we need to go study it for what we're looking at. Then we go make a decision. Did the model of the coffee cup, will it do what we want? Does it behave how we want? That decision helps us determine the next step. And then we share that decision. This is what we did. This is why we did it, so that others can go use it. So that, 6 weeks down the road or 6 years down the road, somebody else knows that if they need a coffee cup, here's what one looks like, and here's how it behaves when you go do things. This key here, this modeling, this simulating, this decision, and then doing it again and again and again is how we design the big systems that were a part of Constellation. Some of them are still being used today. And it's a method that we use to ideally do each job one time, not have people duplicate work, have to do things over and over again and go forward. So our modeling, our simulation, and our decisions that we wrote down and shared with everybody become how we go communicate. Here's an example. The Ares 1 rocket was a thin single solid booster rocket that took astronauts up into orbit. It wasn't intended to go much past space station, but it was also intended to test a large number of things. It had the new solid rocket booster we were going to go use. It had the upper stage engine that we were going to go use, and it had a little bit of every single system that we needed. So we modeled it. We got models that look kind of like what you see on the screen. We modeled all the radios as well. So we took the models from the ground ops organization. Kennedy Space Center had the launch pad, so they had the model of a launch pad. And it was on the right spot on the Earth at the right time for the launch. So you could see how it worked with space station, where it fit in the orbits, where the moon was, where everything else. We had the models from the people that did the rocket, the first part of the rocket, and the booster in the upper stage. And they did all of their simulations and they did all of their analysis, and we set it up so that they could talk to each other. We had the model of the Orion capsule sitting up on top. It gave us the ability to study exactly what it was doing, how it was doing the things that were there, and how it was going to fly. And once the booster was done burning, the Orion flew the rest of the way up to space. We had the abort stage from the Langley Research Center that was doing this. And in case we were testing a failure or something, it was what saved the crew. And we had all the radios being done by the folks at JPL. So this was a simulation that we put together, and we all shared all of the stuff that we knew. And an argument broke out because nobody in the simulation could figure out how to release the bolts that held the rocket to the pad. So we couldn't figure out how to make the sim work. And when they dug into it, they realized that nowhere in all of the designs that had been done and all of the things that had been captured and all of the analysis that had been done had anybody thought about how are we going to release this rocket here from this launch pad when we light this engine, which if we don't release it right away, we'll either take off to space with a piece of the launch pad attached to it, or we'll leave a piece of the rocket, ideally not a very important one, stuck to the launch pad. So our process of modeling things, simulating, making decisions, and sharing everything that we did led us to discover that there was a big mistake had been made, something had been missed, and we needed to go fix it before we tried to launch one of these rockets and it stayed attached to the pad. So these were the types of things we did with modeling, with simulation, with sharing, with making sure everybody knew what was going on. We had another one. I think Luis, this might be his favorite picture, I'm not sure. But from Kennedy Space Center, we had a team that we were working with at the Marshall Space Flight Center. They were building this rocket. And this gentleman here, or lady, had to reach through a hole and do some work inside the rocket. And we would mention that where they put the hole doesn't line up with anything over here. And this poor person's feet they got to go to meters, about 80 meters off the ground, which is it's very difficult to stand 80 meters off the ground. So we would describe the problem, we would go share what it was, we would get the design changed, the rocket would be turned so that this hole was back so the person could stand on a very safe platform. Everybody would be happy. And then the next time we got an update to what the rocket was going to look like, it would be moved back over and we would have this problem again. After this went on for a little bit, my engineers told me about it, told me what the problem was. And I said, give me this picture. And we circled this poor person's feet. And we just sent that picture with the circle around it to the people at Marshall Space Flight Center. And they finally understood because I simply asked them, you know, explain to me again how this person is going to stand here. You know, I can't figure it out. Please share with me what's going on. And the rocket moved back and the rocket never moved. So we used our modeling, we used our simulation, we used our understanding, we shared it, and it solved another problem that was going around. I talk about simulation, but we used things like the previous examples to go in a non-threatening way, in a cooperative way, go work with people to try to tell them that something is not right, something isn't what we're understanding it. One of the things that's difficult is telling the leaders of a project or leaders of a program that something is wrong. If we take this approach, the leadership is not wrong. I just need their help to get our simulation right so that we can understand it, so we can see it. That's usually what happens is somebody knows something that somebody else doesn't. Somebody didn't share what they knew with the people that they needed to, and that led to the confusion and the problems that we had. Or there's another problem here, and that's this one, is that everyone working on this project is wrong. There's something fundamentally flawed, and we need to know that something is wrong right now. That's important. If something is wrong, you've got to go figure out what it is as quickly as you can. The biggest fear I had going through this process, and I watched it happen, and I stayed on the lookout for it through probably the latter half of my career, is if you've got 3 people discussing a problem, it can be 2 people, it can be even more, it's important to them. The worst thing that can happen quite often is that they agree, but what they think of in their mind they've agreed to is different from each of the 3 people. So there's 3, they've all agreed, but what they think is the right answer is still 3 entirely different things. And when that's discovered that, well, no, this person thought this was it, this person thought it was something else, suddenly everyone starts to think they've been lied to. And that really doesn't help the team work together. It doesn't help anybody else go work together because they were, you know, just confused, or they aren't all working on the right thing. And that I have seen happen, and that's something we want to go avoid. Our simulation process, modeling it, simulating the behavior, and then writing down what we did so that everybody else knew it, understood it, including the pictures, is a very, very powerful way to go look at this. We do something similar. We take all of these together with a simulation experience we do. NASA started this with industry, and we've got schools in South America, Europe, the US, Africa, and at one time we had a team from Japan as well, where students took these technologies and they put everything together and they built their base. They built their lunar base to go do what they wanted. And it ended up looking something like this. They built a lunar base. They built a solar system that was correct. You could look in the sky and see Mars in the sky and go fly all the way to Mars to go do, if you wanted to go look and see what things look like on Mars. We created pictures that would show people what things look like. We created math and equations and standards that let us save it. So not only could someone else look at what we'd done, they could also come through and have their computers go work with it. It wasn't just saving the video that happened. We saved all of the math and the results of all of the math so people could go replay it and go put it together. We had one of the teams worked on this small little flyer right here. And they use these tools and capabilities, and they got their engineers together, they got their scientists together, they got their software people together, and they brought in artists to go help them go design it. And they built and designed their entire system and had it to the point where it would have flown in a day. You know, once they built it to that plan, it would have flown, it had been tested, it would have worked in the day. And a major contribution to that team was the artists they brought in. It took all of their ideas and showed them what they were talking about. So we had people together, we share what we're doing, everybody brings a special skill to the table, and everyone works together to go get what they're looking for. So the title here and what I wanted to talk to you about was playing nice with everyone. and playing nice with everyone across every time, the generations that are working now. And in my case, what I've handed to you and what you would hand off to your children or your grandchildren is, first, you have to understand what you're doing well enough to share it. Second, you have to understand what everybody else is trying to do so that you don't harm what they're doing. You don't have to run it for them, but you have to understand what they're worried about. And third, share what you're doing. Everyone else shares what they're doing, and leave a record so people can figure it out. This lets us all work on the same problems. It lets us help each other. And it lets people figure out what happens and what we intended to go do long after people like Lewis and I are gone. Thank you. In the end, working with NASA was probably the 35 years. One of the neatest things I saw is everywhere I went, everywhere in the agency, I found people who knew things I did not know. They were able to go teach me. They were able to go share with me. I was able to go share things with them once I got smarter. And the end result was we were able to do absolutely phenomenal things and get the work done that we needed to go do, and further the science that we wanted to do, further the engineering that we wanted to go do, and leave a record behind so others didn't have to redo all of the work that we did. Thank you.
Hey, Mike, you are learning Spanish, huh? Preguntas, por favor, huh?
I looked it up.
Every
Every little bit of Spanish that I had, I knew it was a very, very small amount, completely went away in Brazil when I heard Portuguese. It all exploded. My brain quit working, and I was done. The Portuguese that I heard broke my Spanish. So we're stuck with this.
Mike and I, we wrote a paper about many of these ideas, and maybe we can share one of these days with you guys.
Thank you so much, Mike. We have learned a lot about simulation and modeling today, and I think it's one of the most important sides of NASA. I would say it's been great. We have a lot of questions already, and so we will leave them at the end of the webinar. And we already have our third guest speaker with us, Laura Segarra. So now we will go and leave the floor to Laura so she can go ahead.
Thank you for having me. I'm going to share my screen. Okay. Can you see my screen with the commercial crew chart?
Yes, now we
Great.
can. Thank you.
Okay, good. So thank you for having me. My name is Laura Segarra. I work at the Kennedy Space Center, and I work with NASA, and I work in the commercial crew program. I have been out at Kennedy Space Center for 19 years now, and it's a very, very cool job, let me tell you. So I've gotten to work, a lot of shuttle missions. I've done an Ares 1X test flight, worked some constellation, and then basically started commercial crew before it was even a program, so in its infancy. So it's a very rare opportunity to see a program from cradle to grave. So I've learned a lot, and I think this kind of trees into the last topic from what I heard as well, kind of applying what we've learned over our 50+ years of human spaceflight and providing that knowledge to private industry. So with that, we'll get into the presentation. See if I can make this thing work. All right. Okay. So this is just kind of an overview of how the different segments of low Earth orbit and our future intentions of going to the moon and Mars work together. They're stepping stones. And really what we're doing at this point, the whole concept of commercial crew was to actually provide our knowledge of a environment, low Earth orbit, that we have quite a bit experience with, and provide all that knowledge and turn it over to industry. And it also serves to bring that human space flight to low Earth orbit capability back to the United States. Because after the shuttle ended, we didn't have a capability of our own. to fly humans anymore. So we were relying on the Russians to fly humans, and then there are other folks that also can fly cargo, but no humans. So that was really where we started with Commercial Crew, and how these are all stepping stones to get to another. So by turning this over to industry and commercializing it, it really allows NASA to go and dive into the more areas of uncertainty, such as the moon and Mars, because there's a lot of things that we need to learn and develop our capabilities. So there's a higher level of uncertainty there. Whereas Leo, we have more experience there. So it's more appropriate to pass that knowledge on. You can use the airlines as a good example of that. In the beginning, the airlines, when it was very uncertain and technologies needed to be developed, the government facilitated that. And as we matured that and developed regulations, it got handed over to private industry. And now it is a commercial running business that everybody uses. So the same intent is here happening now. So that is our intent, to pass all that along. And then we will go and focus and develop and mature these other capabilities to further us get using Moon as missions and Mars. The next chart is just really kind of an overview. It's not, it's just our structure really of how we do this. It's kind of a bit unique because it's really not a hierarchy per se. It's really a flat structure, which is very uncommon. Typically, NASA has a hierarchy and those levels of authority. But because we are doing a commercial model, we knew that we had to make decisions fast. We needed to make them partnered with a commercial entity. And a hierarchy can slow you down if you have too many chains of authority you have to go to. But we do have those chains. But we had to really think about how we would do this efficiently and effectively. So really, we did this by identifying the system elements of your commercial transportation system, and then the integration functions. Of course, you need systems engineering and integration, because what we did, what Commercial Crew did, is we took our time and we established what is the minimum set of requirements that we can levy that makes this safe to carry humans, that we would feel that if they implemented these, which consist of our lessons learned throughout our experience, that it would be safe for humans. And this also gives the commercial entities flexibility on how they want to design their systems as a business. So that's the premise behind our architecture as an organization. So how we do it, it is a partnership. And this model has not been done by NASA before in this manner. It really does require a partnership. So there is risk on both sides put into this effort, money-wise, and of course it's a shared risk of the outcome. So we do have our counterparts that we work very, very closely with. That's the only way to really make this work, because we needed a way to understand how these companies do business, how they do things like configuration management, how they do change control, systems engineering, how they manage themselves as a business and as a company, and also how they go about designing and qualifying and verifying that design that we feel meets our requirements. It's a very much reliant on a partnership there. So with that, again, so where we started with this preceding Commercial Crew, which is for humans, there is commercial resupply service. So that is a stepping stone. So we commercialize the ability to bring cargo to the International Space Station. So that's a stepping stone. It's a very big development activity that basically proves the capabilities of your launch systems and your ability to actually reach to the station. So all your trajectories, they are somewhat proven out. Now you have a new factor that you're bringing in the human. So of course that requires additional systems that you have to design for, and they have to be suitable for protecting humans. We did take an approach that we thought would give the maximum amount of flexibility in these designs to the commercial entity, because these commercial entities, NASA doesn't own these. They don't own the hardware. So the commercial entities they design it, they operate it, maintain it. It is theirs. And the intent is when we're done, we can buy a ride to the station. The intent is at the end, we will say, yes, you have met sufficiently all of our human rating certification requirements, and we have objective evidence that's given to us through 2 demonstration flights. Those flights, one is uncrewed, one is crewed. And as you know, we just completed our first crewed flight to the International Space Station with SpaceX. It was a very successful flight. So we're well on our way. We've made a lot of progress. Like I said, this has never been done before. So we, of course, we're learning as we go as well. So right now, we have Boeing and SpaceX on contract to provide this capability. Let's see, let's go to the next slide. Okay, but this is how we started. We really had to think about our acquisition strategy, as with any program. So since we had never done this before, on the left here, you see this thing called CC Dev 1. These first 3 slots were actually Space Act agreements. They weren't contracts. So we were not levying requirements on the industry at this point. We were really, in the beginning, trying to understand a philosophy, how we could make this work together. We really did solicit their input on how we can make this work, and they did work with us a lot. We held industry days, all industry was invited, but we did have to do a lot of that talking to figure out how can we best make this work. CC Dev 1 was the very initial where we actually awarded specific industry partners Space Act agreements with some money. In the grand scheme of a space flight system, that's not a lot of money, but it's kind of amazing what you can do with that money if your intent is to mature some of their systems, right? So you can focus that on their immature systems and help them get more mature, so that you can look at stage by stage their integrated system. So if you look at CC Dev 2, now we're talking to a lot more industry partners. ATK for a launch vehicle potential. Blue Origin, who you know is Jeff Bezos owns that. Boeing, Excalibur, Sierra Nevada, which is the picture in the middle here. They kind of had a concept of a mini shuttle. SpaceX and United Launch Alliance for the Atlas rocket. So now we're talking to all of them, and they are starting to collaborate amongst themselves. And still, we would set up milestones. It's more like seed money to mature their designs, and they can do more testing because stuff is very expensive. And that's why the government takes on these kind of challenges in the first place, because a private industry could not make money on this. So you would have to have a lot of money that you're okay with doing basically research and development. There's no return at that time. It's a lot of money. And so the third phase of the Space Act agreements was CCI cap. That's where we really got into, okay, here's where you are with your integrated system. This is how, if you were to be awarded a contract with NASA, how you think you're going to go ahead and make this system compliant with a certain pedigree, safe for humans. So it was more like, now we are looking at how they plan to design, develop, operate their integrated system. So it's a step beyond that. It's still at this point, we're not levying requirements. It's still very much a partnership, and we are trying to mature them in areas where they may need help, because all during this time, they have access to all of our engineering. So if they need help developing a propulsion system because they're stuck, well, we can focus our resources on that system to help them where they are stuck. So that's what I mean by partnership. They have access to a lot of our lessons learned and expertise, and that's what made this really beneficial, I think. CCP, the fourth slot here, is actually where we levied the first FAR-based contract. That CPC was the initial contract. It was fixed base or fixed price, and it was really to levy the requirements and tell us how you believe you are going to meet these, like really going to meet these with objective evidence. So we basically gave them our higher level requirements, which are things like, here is the safety requirements for design and construction of pyro systems, for example. It's a lot of lessons learned for humans, by the way. So they would tell us what their strategy is for flowing our requirements, our higher level ones, into their own requirements and flowing it down and implementing them into their systems and providing verification evidence to us. And we partnered those agreements during that time. And then and you can see now we're providing more money. So we did have to down select along the way here. But CCT cap is really where we had to narrow it down to 2. We were hoping we would have at least 2. It all depended on funding, but that's critical because you need competition, right? In this case, if you're trying to commercialize, you really do need the competition factor in there. And that's what we got. That's where we're at now. So we did down select to Boeing and SpaceX, and that is where we are now. I mean, it's amazing what we have done with this kind of money and this kind of time, but it really was dependent on a strong partnership and the shared risk approach. For example, we also implemented a method of a hazard assessment that gives the commercial entities maximum control or say over their design, however they want to implement it, but it assures they are protecting for catastrophic hazards that could, end in either loss of mission or loss of crew. So that was one of our strategies, but it is a very high level requirement, but it really makes them look at their design and look at what can go wrong, all the things that can go wrong that could be catastrophic, and protect for them. So that's been working actually really well, especially where we have an existing design, such as the Falcon 9 for SpaceX and the Atlas V for ULA that Boeing is using. We mainly relied on the certification of that launch vehicle through the hazard reports, through the hazard process. So let's see. Oops. I have not figured out this button here. All right, here we go. So this is just kind of a breakdown of the elements of these vehicles. I mean, I talked about them at a high level, but the Boeing has the spacecraft, which is the CST-100 Starliner. They use the ULA Atlas V, so that is a partnership between them, but Boeing is the prime on contract with NASA. They use a Launch Complex 41 out on the Cape Canaveral Air Force Station. And then they land, their plan is to land their vehicle, their spacecraft on land with parachutes out in New Mexico. And SpaceX, they have the Crew Dragon and the Falcon 9 launch vehicle. They launch crew out of Launch Complex 39A, which is actually the old shuttle launch pad. We have 39A and 39B that we would launch shuttle from. And then they have to land in the ocean. So here's a status of where we are right now. So we did 2 uncrewed flight tests. This is all part of the certification. The flight tests are crucial to understand, did this do what we thought it was going to do? And plus there are some things that you cannot test on the ground sufficiently. So this also gives you an opportunity to see the integrated system and operations at work, because the objective is we want to set these companies up to be able to conduct missions on their own. So we have made quite a bit of progress here. As you can see, Boeing has an orbital flight test number 2, and that's because the unmanned flight test that they did in December did not make it to station. We had some issues, but this is exactly why we test. right? Because you want to drive out those issues, you want to understand and you want to learn from them and move on. Fix it and move on. That's exactly why you do that, because there are things that you cannot predict when a big integrated complex system like that works together. So that is where we are right now. It was pretty amazing to see the SpaceX Crew demonstration, because that was the first time we've launched humans from US soil since Shuttle, so over a decade. So that's pretty historical, and it's never been done ever through a commercial mechanism, never done commercially. So they also, once they are certified, after their 2 flight tests, we will then assess how well they met our human spaceflight requirements, and we'll grant them a NASA certification to carry NASA astronauts to low Earth orbit. And then they can get into post-certification missions, because we still need a presence on the International Space Station. So we have an opportunity to buy that service from them. All right, and so here's the crew. So you know Bob and Doug here. These are the astronauts that just flew and landed successfully. But we've also selected the crew for the post-certification mission, which is called Crew 1. That's what SpaceX calls it. They have a lot of cool names for their hardware and pieces of their vehicle. And then here is the Boeing crew flight test manifest. And then once they are certified, Josh and Sunny will fly on their post-certification mission. So the reason we select them is because it takes a lot of training and practice and simulation with the astronauts. This is the first time for these companies too. So we really got to practice with the operator, the human in the loop. That's a very crucial thing, because if you think about it, if you are sitting in a pilot seat and you kind of got it wrong and you can't see or reach the buttons that you need to carry out your mission, well, that's not good. So there's a lot of training and contingency. What do you do? What systems do you have? What is the protocol if certain things happen? So there is a lot of practice in it, and it's not just the astronauts. It takes a very big team to do this. You have people in mission control. You have people staged in different recovery sites in case you have to abort. So there's a lot of contingencies to consider, and you have to make sure that your vehicles can perform to execute those contingencies, because typically if you need to abort, it's a maneuver that is quite, depending on when it happens, it's a maneuver that is quite stressful to your structure, to your vehicle. So you need to make sure that it can do those things. And so for both of these companies, they did abort tests for us to prove that, yes, if we needed to abort, we can do that, and our vehicle can handle it, and we can successfully land and save the astronauts. So here's some pictures of the joint simulations and practice runs. So there's some pictures of practicing recovery operations here. We partner with the Department of Defense for rescue operations, as well as the Air Force. This is actually a NASA MRAP, basically kind of like a little tank in the back, which was actually used to go recover some stuff in a hazardous area when we did have one slight mishap testing some thrusters on the SpaceX spaceship. But again, that's why we test. You want to drive out those failures before you put people on them. But you can see this is a pretty large breadth of operations going on here. So they're testing, I mean, even down to putting the suits on. You have to time those things very precisely, especially with a company like SpaceX, because they only have a certain window where they can actually launch you, because of the way that they have implemented their operations. So you need to actually know your timeline, and you need to practice it to make sure that you can execute it and you can load the crew in when you think you are going to load them, and execute your mission. And these are all instantaneous launch windows to the International Space Station, which means you have to launch at that instant to catch the space station. So if your timeline's off and it took too long to load the crew, well, you're not going to station today. All right. This is just trying to point out that the build, test, fly that I have been talking about. This is how we learn. You have your concept that you mature it, and you build either your engineering article, prototype, whatever you want to call it, test it, learn. But you definitely, you test like you fly. You want to expose this hardware to the environments that you expect. And when you do qualification testing, not only those nominal environments, but plus some to make sure that you've got margins in there. So they have done this for their vehicles, which is a lot of work, as you can imagine. It takes some specialty facilities. If you can see the engine testing right here. What's cool is that, you know, these commercial entities, especially if they own the facility, they can test because they have the capabilities in-house to do it. And even if it messes up and say they do a little damage to stuff, they can recover very quickly because they have the resources and the capabilities in-house to do it. And so they do rapid testing and turnaround and what did we learn? And we'll do our upgrade to our design, and then we'll test again. So it's pretty impressive. And then over here, you can see the end line of the Falcon 9 production. That's pretty impressive production site as well. So our certification does cover design, test, evaluation, manufacturing, and operations. All of those phases, because again, we do want to set them up to conduct missions on their own. All right. We already went over this status. So what's really next for SpaceX, since they did the crewed flight test, is now we're reviewing the results of that flight test. So you get the hardware back, you inspect it. Did it behave like we thought? So there's a lot of trajectory data and things like that that we are analyzing. We're inspecting the hardware. Is there any signs of damage? That kind of thing. We're looking at all of those things and basically assessing how our operation went. Is there lessons learned? Did something not go quite right how we thought it was going to go? So that we can, again, learn, because it's the first time we've ever had crew interacting in this as well. So that's where we are with them. That's the next step, is to fly the Crew 1 flight, and we are assessing whether or not we feel that we can certify them, how adequately NASA feels they met our human spaceflight requirements. And it's really a risk-based approach. We assess the risk to the crew based on meeting all of those requirements with objective evidence. And then Boeing, so their next up is to do the orbital flight test number 2, which is unmanned. So the plan is to dock to station autonomously. Neither of these companies have ever docked to station. So that's quite a feat right there. And then after that, they will do the crewed flight demonstration test and so forth. But pretty cool photos. That's a lot of work right there. All right. There is just a little video. Because the point of this is that we are continuing our partnerships with other commercial entities through the Space Act agreement. So they still have access to NASA expertise, information, documentation, and then we will support with our experts things like this. Release. This is out at Edwards. Well, it's not Edwards anymore. Pretty cool. So they're doing a drop test, and they're basically testing out their autonomous flight. Can the vehicle respond using the flight computer and the software that they have selected Can they prove some things and learn some things from their guidance, navigation, and control? And look at that, pretty cool. And you can see at the beginning of the video that they took a nosedive because it's trying to get some speed so it can control through its aero surfaces. So pretty impressive. And Sierra Nevada does have a cargo contract with ISS to fly cargo to the ISS. So they still are also working with NASA in that respect as well. All right. So I think we already talked about this, but, you know, again, the intent is for us to provide a more regular and a reliable transportation system to low Earth orbit. And then the companies can use that, not just for NASA. This is just an opportunity. It's a need for us, and it's an opportunity for us to provide this new design reference mission to them as well, to further the commercialization effort in general to low Earth orbit. And again, NASA can go and use our resources rather than in LEO, low Earth orbit, to go work on getting us to the moon and Mars to further our space exploration. So that is what we're doing. Yeah, this is just where you can find, there's also a Flickr account. There's some really cool photos and videos on here if you would like to go check it out. And that is all. Are there any questions?
Thank you so much, Engineer Laura. It's a pleasure for me and an honor to be here with you as a woman trying to get into the space industry and listen to you talking about one of these topics nowadays that we all want to know more about it, and the future projects that you have told us. It's just amazing. We have many people, many of the participants interested in this topic as well. In one of the courses we are given, the introduction to space engineering, we were talking about the commercial crew, and also we even did the streaming of the splashdown of SpaceX launch.
Yes.
Yeah.
How exciting, how exciting.
I was definitely excited. So yeah, we have some questions already here, and I would like to read them. We have many participants here interested in each one of the topics you all were talking about. So yeah, I will go ahead and read them. So we have the first question. It says, if I'm interested in...
I think Roxy just dropped out. Let me take the question myself. So the first question is for Mr. Mike from Herbie Castro. Hey, Mr. Mike, what would you advise to an undergrad student who wants or is trying to get an internship at NASA?
Oh, well, actually, NASA has internship program, and they have a website. If you just put into Google NASA internship, you should definitely apply. It's very unique opportunity. I've had several interns myself that I have mentored, and what we will do is we'll try to give you a diverse experience with the different types of entities within NASA. For example, we would give you a program experience. I work in a program, what that's like, versus being in engineering and looking at a specific discipline you may be interested in. So there's a lot to share. I highly recommend that you apply. And there's even a new internship program where they will actually have you spend time at different NASA space centers, or NASA centers, so you can experience more than one center now. So definitely go to the website and check it out and apply if you are interested in that.
All right. Roxy, ¿estás ahí?
Sí, ya volví. I'm here. I'm back. I lost connection for a while. Perdí la conexión por un ratito. Yeah, so we will go ahead with another question. I listened Angel reading the question about internship. So I will read another question related to NASA, and this is addressed to Dr. Rabelo. It says, do you have an average for researchers or collaborators?
That depends. I remember that when I worked in the Tiger team for the NASA shuttle flight problem, we were 150 people with PhDs. And I went just with a student from UCF, and we worked with that team. 150 PhD, 150 different personalities. Therefore, yes, it can be very little to hundreds of collaborators.
Okay, thank you. We have some other questions here. Tenemos algunas otras preguntas aquí. Muchísimas gracias. Let me see. Okay. We have a question for Laura. So they say, hello, Mrs. I would like to know how difficult it is to define the organization of each project. What elements do you require to define the roles and also the tasks that each group or member has to functionally accomplish? Do all respond to any type of motivational system in order to boost proficiency in order to not delay the progress of each project? So now I'm going to read it in Spanish. Hola, señorita Laura. Me encantaría saber qué tan difícil es definir la organización de cada proyecto, qué elementos se requiere para definir los roles y también la asignación que cada grupo o miembro tiene como funcionalidad lograr. Todos responden a cualquier tipo de sistema motivacional en lugar de poder mostrar proficiencia para poder no retrasar el progreso de cada proyecto.
Yeah.
That was a long question.
Well, it's a very good one, and I'm glad that was asked because it's a very important thing to consider before you go execute something like this. And Commercial Crew was very lucky because it was the first time, and we knew that we needed the best when we were going to do this because we knew that we were not going to have this huge budget, right? But we knew that we would have to be working with a commercial entity, which their pace is a lot different, but they're also taking a different level of risk. So you really got to consider that, which is why we basically broke ourselves down to reflect the system and the integration functions, as I said before. Now, what is different is that these systems are part of the program proper. So there's a spacecraft office because that is a major element. You try to model your workforce that in a way that is going to basically the best you can eliminate duplication, overlap, and that actually lines up with your vehicle system as well. So if you look at a vehicle system, there are major interfaces between the launch vehicle and the spacecraft. That's a big interface, but that is where you can separate because the connection between them depends on the design, of course, but it should be minimal there. Whereas within the spacecraft, there's lots of interdependent systems. Same thing as how we structured within a spacecraft office. There are many people that have to have specific skills and disciplines. You have to have electrical power, fluid systems, ECLIS, environmental control, life support, all of those things that have to work together and communicate with your ground systems and all of that kind of thing. So what we have done is in the program proper, we created the offices and they are the authority. And then you have a matrix of expert discipline engineer tech authorities is what we call them, but it is a mixture of engineering, safety and mission assurance personnel, and human health and performance. So those are the main tech authorities. There are also another kind of branch of that, which is flight operations. They are the experts in flight operations. And the reason that we have designed teams like that, usually these engineering and tech authorities are in the program proper, but we needed to move fast. They needed to be able to reach back to their experts as well. And we needed to have more of a matrix structure on a very detailed working level, but we also needed the best. So that is how we implemented them. So they are basically matrixed, but dedicated, if that makes sense. But they are the experts, and that's the only way we are able to do this, to accommodate a pace that would be somewhat acceptable for partnering with industry who has a completely different pace. So in essence, that's really the thought that went into the structure. And within that structure, we don't actually have projects. Like I pointed out before, it looks like a hierarchy, but it's not. It's a flat structure that relies on collaboration between those elements, those offices, and you have integrators that collaboratively bring all that information together and make sense of it. And then ultimate authority for decision-making on the NASA side is the program manager, of course. But it relies a lot on cooperation, not so much on I am in charge of this, not so much the hierarchy, but that gives us, again, the flexibility, our ability to develop things organically and do that with our industry partner as well. And within that structure, we have also, and it's not written, but we have a team that is dedicated to Boeing and a team dedicated to SpaceX. Now, on the lower level, the experts, because there's not a lot of experts in certain things, we can share those, and that's worked out pretty well. But if it's something that is a system that is immature, a lot of work, or there's a lot of risk involved, you need dedicated people or a lot of integration. So you look for the overlap. Where there are interfaces, if there's a lot of interaction between those interfaces. And that's how we chose to basically segregate our offices that matches the system with the integration functions. Now, of course, you have a program control function, which is basically like project control, but in a program, you're taking care of a pretty big workforce, and you have to provide things like training and infrastructure, like an IT infrastructure. There's all kinds of things. You have the money people, but they're all in your program control schedules, all that kind of thing. So you have a separate office that basically is the backbone to your program. And it will also do all of your config management and that kind of thing. But it is the backbone to how you go about making decisions as a program. Does that answer the question? I know it was a long question. I hope I hit it.
Yeah, I think so.
Okay.
I think so. Very well.
Right, thank you, Luis. And I don't know if Roberto Roy is also unmuted, if you would like to make your question live.
Can you hear me?
Yes.
Yes, we do.
Yeah. I just wanted to know when is the SpaceX Crew Mission 1 going to launch?
Right. So we are actually assessing that right now. I think that the last published date may have been September, but we are looking to move that out a little bit. So I can't say for certain when it's going to be. All I can say is we will fly when we're ready, when we're confident that they have met these requirements. But so my best guess would be, late October at the very earliest, because it's a lot of work to do that, to provide a certification like that. And we're still processing the post-flight data, right? So we got to get through all of that as well. So I can't say for certain, but that's what we're trying to achieve.
Thank you.
I think you are trying to go to the stock market to send some money to Tesla.
Oh, not me. I just work for the government.
Right, Roxy?
Sure. Yeah, I'm reading some other questions, and let's see with which one we go. So we have one question which is related to a lunar base. So maybe Mike can answer us a little bit more about that. So it says, is it planned to install a lunar base, and in what moment, and how will it be the simulation or modelation of that sense?
Okay, the plan all along, when I was there, and I believe the plan still now, is we're going back to the moon, but the intent is to go back to the moon to stay. So that is a base. Where you put your base, how you go lay it out, how do you, as we learn more and more about the moon, what resources are where that we want to be next to, and how do we go move things around and get the resources we need, is all being worked out. The tools they're using are simulations, and it's almost like if you look at a game that you're playing where if we do this, 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 and this, how is it going to go work out? But instead of running it on your local computer, you're running it on a very, very large computer that's helping you figure out what the answers are. The tools and the displays that I showed that the students are using for their lunar base are the old versions of what NASA is using today. Team members I've got that help us go do that are the ones doing this exact same work for NASA today. We just do it as an educational program as well. And it's a relatively good way to test your software, because if anybody is going to go break your software, it will be a bunch of college students. They will find out exactly what you did wrong, and they will uncover exactly every weakness. So we've been testing things that way for about 8 or 10 years now, and it worked out really, really good.
Hey, Mike, one of my Latino students, David Miranda,
Yep.
worked for you, and I think he replaced you in your...
He's doing sim work out there as well. He's got his focus is a little, Kennedy's not playing in the base operations activities as much anymore. But David's fantastic, and he's doing a lot of the discrete event type work, a lot of the system engineering type work, a lot of the process analysis type work for those same projects. It's phenomenal. David's a good one.
Yo le estaba diciendo a Mike que uno de mis estudiantes latinos, David Miranda, trabajó conmigo en un proyecto con NASA, y después la NASA se lo llevó y trabajan en simulation and modeling en NASA.
That's another example of you want to always work around people that are smarter than you are. It works out really good in the end.
Yeah, great. Okay, we have a question from a 12-years old from Panama. If you can explain why commercial crew name, what is the name of why the name is commercial crew for Latin America? Sounds like Grupo Comercial.
Right. Well, it was named Commercial Crew because of our intent. Our intent was to commercialize low Earth orbit, basically mature that capability and provide that to commercial private industry, and crew because we want them to be able to carry humans, crewed flight. So that's why we called it that.
All right, thank you. Good. Roxy?
We have another question in the chat, and I think this question is really funny maybe, and really interesting, because it says, it comes from Luis Diaz, and he says, what will you consider to be more complicated, to do engineering job or manage people?
Oh yeah, that's a good question. Right. I mean, the technical job itself, of course, does require you to work with people, but managing people is kind of a different game. So what's harder? Oh boy. I think that would depend, but in my personal opinion, I think managing people is much harder because they're a bit unpredictable. You don't have so much control, whereas if you are designing and developing, you kind of know what your parameters are and you can somewhat control those. So yeah, I think it's the uncertainty factor with people why I say that. So that's just my opinion.
Let's see what the other things. Let's see, Mike, what do you think about that question, and Dr. Rabelo?
The projects are fantastic. Working with the people is also fantastic. I believe Laura's right. It's a bit more of a puzzle, but when you solve it, when you can get things working, and kind of the theme I was talking about is you get to the point where you can teach and mentor and help a lot of people go succeed and go tie things together, it becomes you can get a lot more done that way. And part of it too is you want to leave behind not only a record of what you did, you want to leave behind people that can do as much, or ideally even, you want to leave behind people that can do more than you were able to accomplish. And to me, the best way to go work that was to go down the management side of things. Plus, like I mentioned, I didn't really have a choice. I woke up one morning and suddenly, yeah, this is your new job, go do it. But I really didn't want to go back. It's the bigger challenge is the leadership, the management, the bigger reward I think is on that side too.
Yeah, I would have to agree with you too, because I think there's several levels there, right? So you can be very discipline centric in engineering, but you can also be more of an integrated engineering, multiple systems. So if like a level up, of course you have to work with people, but then there's things like leadership. Like I am an integration lead. I'm not a manager, but I rely on cooperation. So I set the direction, but I am hoping I get cooperation with that, right? But I think, like you said, you in a leadership role, which is a bit different than management. I don't sign people's time cards and have to do that piece of it, but it gives you a very good opportunity, like you have said, to mentor, to develop people, to give people opportunity, So I think that is the cool part. And when you get a team that functions together like that, and they are cooperating, I mean, there's nothing they can't do, right? So I think that's pretty cool.
Una de las organizaciones más de mentorship es NASA. One of the top organizations in mentorship is NASA. If you want to learn something, there is always training. Si usted quiere aprender algo, siempre hay entrenamiento. Usted es un trabajador de NASA, quiere irse 2 años a estudiar un doctorado a la universidad, váyase, se la dan y le pagan la universidad entera. Cualquier universidad. And if you want to study more, there is universities. Si uno es un top manager y se quiere ir 1 año a Microsoft, se lo pagan. There is training about ethics, training for everything. And it's an amazing organization from that viewpoint, from the mentorship.
Thank you so much. All right, we have another question from Luis Angel from Nicaragua.
Hello.
Yeah, go ahead.
Luis Angel here. Well, my question is about, is there any considerations to build up like supportive suits armor in order to enhance the space activities, or even the Earth activities, having certain research being done in the spatial station? And also I would like to know that if it's in the possible future that we already have colonies in Moon and Mars, this could be a reality, or this could be a project that is already on a study, or it is not yet planned. Thank you.
Right. Do you want to take a crack at that, Mike?
That one's yours. Actually, no, from the spacesuit side, there's a great deal of work being done. If you looked at the 2 recent astronauts that just came back with commercial crew, they had a very, very different suit than what NASA had. There's an intent to go forward, and there's an intent for the lunar suits to go be very different, because the difference there that's a challenge is they have to be able to take the suits on and off, not like the last time we were up there. And the processes involved with that, and the amount of dirt and dust and everything else, is leading to a lot of innovative new ways to go look at it. And that continues. There was talk of suits for EVA space operations. There's talk of new lunar suits. We have people at our institute that are working with the different NASA teams on ways to make the suits for the moon surface simpler. So that work continues and keeps going on.
Thank you to all of you. We have another question, and I think this will be live. So Alejandra Solis, maybe you can ask your question live.
Okay.
Hi. Do you hear me?
Yes.
Okay, sorry. Hi from Costa Rica. Working in NASA feels like a dream to me. So what tips will you give to university students like myself that would like to achieve this dream? Do all types of engineering work at NASA? Thank you.
There are all types of everything. Dr. Rabelo mentioned the number of different PhDs that were there. On the engineering side, I worked with or led or managed every discipline that I knew of, and some that I think were invented while I was out there. For a university student, the first thing to do, I would say, is talk to the faculty or the offices that are available at the university and see if there's programs for that. The sites that Laura mentioned for internships, I was a part of what was considered the co-op program back in the 80s. And it's done rather different now with the types of internships that they do. But the ability to work out there either with NASA itself, which sometimes has some restrictions, or with the different contractors that are out there, that's the way I got in. And that's the way that, that's what I'd recommend for a student. If that doesn't work, give me a shout. We also do projects where NASA teams propose challenges, and we work with student teams at different universities to go solve those problems and then report back to the NASA folks how they solve the problems. But university first, the sites that Laura was talking about as well, just to see what's available there and how that works. And if neither of those work, contact me. I think the slides will get posted, and my email is on the front slide, and maybe we can put together some teams to go work on some projects with your university.
Very cool. I think a key thing that I would mention too, I mean, don't give up. If that's really what you want to do, make it happen. I mean, hey, maybe right off the bat, you don't start working with NASA, but I mean, all the experience is just more experience on your belt. Keep trying and get what you want, because you can do whatever you want.
All right. We have a last question, maybe for each participant. You can reply quick. From all of your experience and work you have been part of, which one do you feel the proudest? And what do you think is the most inspiring? Let's go ahead with Laura first.
Can you repeat the first part of the question? It dropped out a little bit.
Yeah, from all of your experience, which one do you feel is the proudest?
Oh boy.
Most inspiring.
Well, I think this last mission probably was the proudest, because again, this was a lot of work. I mean, it wasn't like work that's contracted out and you oversee. This was a lot of work that we very actively participated in and partnered, and nobody's ever done this before, and it was very historical. So I think that's the proudest, for sure.
Perfect. Mike?
I would say the work with Constellation. What we did to tie all the NASA centers together, to do the testing, to figure out that from an engineering point of view, using simulations to go verify that you didn't miss anything. That was the first time that had been done. We were able to tie together all the NASA centers working together. We were able to tie in the European community and ESA and other space agencies to be able to go look at stuff. Being able to let everybody go look at things and go make, I don't want to say mistakes, but go to be able to discover what we were doing that probably wasn't the best before we built anything was absolutely grand. I've had people tell me that they're still, that's the thing that the coolest thing that they worked on, or the coolest thing that they were a part of. And looking at the calendar, we did that 10 years ago. So it was, that was to me, the work we did there, that all the NASA centers did there at the end of Constellation was fantastic. That was the most rewarding.
Okay, thank you, Mike. And Dr. Luis, maybe to finish the webinar.
Well, fue miembro del Tiger Team, trabajar con Discovery. When I was member of the Tiger Team, to work with Discovery. And, y después de un par de meses, ver la cosa volando. No hay nada igual como ver el shuttle saliendo. There is nothing equal to see a launch of the NASA shuttle. There is nothing equal. The experience is beyond. La experiencia es más de lo que ustedes creen. sentir, estar a kilómetros y sentir la tierra remeciéndose como un terremoto, estar a 4 kilómetros y sentir el olor del combustible, to be a 4 miles and to feel the tremor on the earth, the sound wave, and also to even smell the fuel. It's just an amazing experience. It's just, I know that Mike watched the Apollo 8. That means the Saturn was.
There's no way you're old enough to have been around for that one, so I apologize for pointing that out.
Apollo 8, en Apollo 8 debió haber sido espectacular que Mike pudo verlo, los Apolo, porque esos cohetes eran, pero ver el show y después de estar trabajando debajo del show, después de regresar y trabajar debajo y después verlo volar. Digo, lo que uno trabajó o lo que uno vio y después verlo volar, it's just amazing. It's just amazing.
Yeah, I agree. I miss those days because that's some serious power, right? Like you say, that thing launches, all the car alarms go off, right? And then if it's night, it's as if the sun came out. It's amazing.
En la noche, ver uno, yo vi varios de la noche, espectacular, con la luna atrás y saliendo el show del este, se alumbra todo alrededor.
Great, great.
Wow.
All right, it's almost 2 hours in the webinar, very, very long. Thank you, I appreciate your participation. Roxy, some final words?
Yeah, sure. I am just impressed. It's just as many of the students and participants said in the chat that their dream is to come to NASA. That's one of my dreams too, either come to NASA or any other space agency. So listening to each one of you, it's been really inspiring, motivating, and I hope we all can keep in touch. And I want all the participants to know that we are doing a lot of collaboration with Nika Woman Tech as well, which is an organization that promotes a lot students inclusion, women inclusion in the space industry and technology itself. So I'm so thankful and honored to be able to be a host for this webinar and to work with Angel.
Yeah, thank you, Dr. Luis. Thank you, Laura, Michael, muchas gracias. I guess you improve your Spanish a little bit.
Just keep me away from the Portuguese. It blows it all up.
Thank you so much. And
thank you, Mike. Thank you, Laura.
Thank you, Laura. Thank you, Mike, for being part of this.
Everyone have a great evening.
Have a great
Have a great
Latin America.
Bye.
Bye.